To begin our discussion of probability, we need to start with a few definitions. First of all, we need to discuss the concept of a statistical experiment. When you think of an experiment, you probably think of a white lab coat or something very scientific, but an experiment in its very simple form is just a process, a random process that yields an observation whose outcome is not known in advance. So flipping a coin would be an experiment. When you flip the coin, it could land on heads or tails. You don't know which outcome you're going to get whenever you actually flip the coin, so that would be a random experiment. Giving someone a new experimental drug would also be a random experiment. You give them the drug, you don't know what kind of outcome you're going to get. The drug may either be effective and help to improve their symptoms, or it may not work on them at all. If you select an item from a manufacturing process, that item may meet certain specifications or it may not. So all of these things would be considered random experiments or statistical experiments. An outcome is just the result of an experiment. So if you flip a coin, the outcomes would be heads or tails. If you give someone a particular type of medicine, the outcome would be they either see some improvement in their symptoms or they don't. So outcomes are simply the results of an experiment. An event is just a subset of outcomes that might be of interest. So it could be a simple outcome, such as someone is feeling better after taking the medicine, or it could be a complex event that involves more than one outcome to produce a desired result. And lastly, the sample space is just the set of all possible outcomes of an experiment. So when you do that experiment, when you execute that process, what are all of the possible results from executing that process or conducting that experiment? I try not to spend too much time doing examples where we're rolling dice or flipping coins, but in these early discussions around probability, sometimes those things really do help to illustrate the concept. So suppose, if you will, we have two die. One is labeled D1 and one is labeled D2, and so you can see in the pairs of columns here all of the possible outcomes for D1 and D2. And we can identify or distinguish between these two dice. So for example, a 1 on D1 and a 2 on D2 is different from a 2 on D1 and a 1 on D2. So we have all of the possible pairs of numbers that could occur when you roll these dice. And you can see a list of all of these possible outcomes. So one outcome might be a 1 and a 1 or a 1 and a 2. Those are individual outcomes of the experiment, and the list of all of the outcomes would be the sample space. So what we see here on this screen is actually the sample space for rolling a pair of dice. A simple event might be rolling a 2. There's only one way that you can roll a 2, so that would be a simple event. A complex event, on the other hand, would be something like rolling a 5. There are 4 possible ways that you see highlighted here on the screen to roll a 5. 1 and 4, 2 and 3, 3 and 2, or 4 and 1. So 4 possible ways to roll a 5. Rolling a 5 would be a complex event in this particular scenario. Based on that, once we have the sample space, we can compute probabilities. And a probability of an event is simply the number that measures the relative likelihood that that event will occur. Probabilities are always between 0 and 1. So you can never have a negative probability, for example, and you can never have a probability that's greater than 1, which sounds obvious, but when you're working probability problems, if you happen to end up with a probability that's greater than 1, that is a signal that you've probably done something wrong and you want to go back and review your work. So make sure when you're computing probabilities, those probabilities should be between 0 and 1. And if you add up all of the probabilities for the sample space, all of the possible experimental outcomes, those probabilities have to add up to 1. So for example, if we looked at the probabilities of each of these pairs of dice, each of which are equally likely, so out of 36 possible outcomes, the probability for a single pair, for a 1 and a 1 for example, would be 1 out of the sample space of 36, or 1/36. And if we add up all of those probabilities will add up to 1. So I just illustrated one way of assigning probabilities, and that's the classical method. The classical method simply assigns probabilities based on the assumption of equally likely outcomes. So you list all of the outcomes, they're mutually exclusive, they're non-overlapping. You assign a probability to each of those outcomes by taking the number of occurrences divided by the total number of observations or the total number of outcomes in the sample space. That's the classical method. And that's what we typically think of if we're going to compute a probability based on numbers or based on data. The relative frequency method assigns probabilities based on experimentation or historical data. And often we think of this as a long-run frequency or the law of large numbers. So for example, we know that if you flip a coin, there's a 50-50 chance that you land on heads versus tails. However, we also know if you flip that coin 3 times or 4 times, you probably won't end up, if you flip the coin 4 times, with 2 heads and 2 tails. But in the long run, if you were to continue to flip that coin, if I assigned you the task of flipping that coin for the rest of the day, and you flipped it hundreds of thousands of times, then in the long run that probability will settle down to that expected value of 50% heads and 50% tails. So that's the relative frequency method. The subjective method simply assigns probabilities based on judgment, and so that could be based on historical understanding, based on some sort of maybe scientific interpretation or some sort of business rules that will give you an indication of what you expect the probabilities to be in a particular scenario. We'll focus primarily in this course on the classical method when we are actually required to compute or assign probabilities, because we're going to do this from a very database perspective. The next thing we need to do is establish some basic relationships that occur when we're thinking about probabilities. We're going to take a look at some definitions here, and then we'll actually draw some Venn diagrams to help us visualize what these relationships look like. So first of all, the complement of an event A is just everything that is not in A in the sample space. The union of 2 events would consist of all of the outcomes that are in A or in B or in both. The intersection, on the other hand, are all of the outcomes that are in both A and B at the same time. And we say that 2 events, A and B, are mutually exclusive if they have no outcomes in common, or that intersection is empty. So if we were to think about drawing a Venn diagram, well, let's start with thinking about the idea of a complement. Suppose this rectangle represents the entire sample space, and inside of that rectangle we have an event A. Then the complement of A is everything that's not in A. So in particular, all of this stuff out here is what we would call A complement, right? It's the stuff that is not in A. So we have A and we have A complement. If we think about looking at the definition of a union between 2 events, suppose we have an event A and an event B. If we want to talk about the union and the intersection for A and B, there's our event A and our event B. The intersection is everything that is in both A and B at the same time. So the intersection is this overlapping bit, right? So that's the intersection between A and B. We could write it as A intersected with B. The union of A and B is everything that's in A or B or both. So that would be everything in A plus everything in B, all of those outcomes, and that would represent the union. So A union with B. We sometimes say that as A or B, and that would imply A or B or both. When we talk about the intersection, A intersected with B, we typically say A and B, that joint overlap between A and B. And then the last definition we had was mutually exclusive, and 2 events A and B are mutually exclusive if we have an event A and an event B that have no outcomes in common. So in that situation, A and B have no overlap, right? There's nothing that's kind of overlapping between the 2 events. They have no outcomes in common. The intersection is empty, and so in this situation we would say that A and B are mutually exclusive events. So having established those basic relationships of probability and some terminology and definitions associated with probability, we're now ready to begin to look at some probability rules that will allow us to compute some more complex probabilities and solve some business problems.